So we're going to look at a particular dehydration reaction. You'll remember that dehydration reactions are a type of elimination reaction. So this is like opposite of an addition reaction. So remember our addition reactions where we added across the double bond opened up and added like each part of that, the part that had been originally a part of the double bond, each one grabbed onto a new molecule, so we added to it. We're having the reverse. We're eliminating those two things. We're actually going to lose something, and it's called a dehydration reaction a lot of times because we're losing water. So that, OH and H is dehydrated, but we're eliminating two things, and we're going to close that drawbridge down. So as you've seen in your other dehydration reactions, we can dehydrate an alcohol to get an alkene in the same way that we were able to hydrate an alkene to get an alcohol. So they're just kind of a reverse. Now, if I go to complete this dehydration reaction, I'm going to notice something that I haven't seen necessarily before. So in a dehydration reaction, remember we're making water. So that's what we're going to lose. That's what's eliminated from the molecule. And we're going to, close a double bond. And we make that water molecule by taking an OH from the carbonyl carbon, and then an H from the carbon that's adjacent to the carbonyl carbon on either side. So when I look here then, so not this carbon, it's kind of important to note. So I'm gonna, the OH is gonna leave, and then essentially then it's one of these hydrogens, because this is my carbonyl carbon right here. And the hydrogen in a dehydration reaction comes from the adjacent carbons, a hydrogen from one of these two, not this carbon. If we lose this, that makes something completely different. That's a different kind of reaction. With a dehydration, we're looking at either this or this. We're going to lose one of those hydrogens, but that's going to put our double bond potentially in two different places. Well, think about it. If I lose this one, so let's say this hydrogen leaves, there's a little H leaving, it's going to go and it's going to make water. And sometimes we include that. I'd encourage you to when you know that water is lost through the process. So there's our water. And then this comes down, so we're going to get plus CH3, and then our carbon is still there, and we've lost one carbon. Whoops. We've lost one carbon, and we've got a double bond now here between our carbonyl carbon. We no longer have the OH group. We have the hydrogen still, and then we have that final CH3. If you want to expand this out, it can be a little bit helpful to look at it in an expanded form instead of in the condensed form. Now, that is actually a different isomer than if the hydrogen is lost from here. So let's kind of rethink this. If instead the hydroxyl group grabs, and we're not going to get into the mechanism by which it actually happens, but instead grabs this one, we are going to end up with CH3, CH2, and there's our carbon. That was our carbonyl carbon previously. It still has its H, but it's double bonded on this side, and we're down an H, so we had to lose that hydrogen. Now notice these are not the same structure. We have, this would be 1, 2, what do we have, butene, and this is 1 butene. 1, 2, 3, 4, yep. Making sure. So we have a situation where we have two potential different products. And if you think about it, this probably doesn't surprise you, because that's actually what we saw when we hydrated alkenes, because it was an unsymmetrical addition reaction. We had to consider which one was the major product when we added across the double bond. And so when we do essentially the reverse, when we remove this in an unsymmetrical way where somebody loses the hydroxyl group but somebody else loses the hydrogen, we're going to sometimes have a situation in this unsymmetry where we have different products, and we might be asked then what one is produced more often or more likely, because, as probably not surprising to you, it's not a 50-50. Just like we saw with Markovnikov's rule, nature seems to prefer a certain product over another, one of the products tends to be more abundant and more stable. Now, we can't use Markovnikov's rule because Markovnikov's rule is about the the addition of a hydrogen. Sorry, I had to think about it. This is about the removal, but another chemist noticed a pattern, so the rule is named after him. Zaitsev's rule states that in an elimination reaction, the alkene with the most alkyl groups on the double bonded carbon is the major product of the reaction. So what we're talking about here is when we look here, we have this. So if I want to think about my structure this way instead, because that kind of helps me visually, I have a hydrogen here, and then I have a CH3CH2. You'll notice in my double bond here, I only have one alkyl group, this one, because these are all hydrogens. But down here, if I wanted to redraw this, going this way, I have an alkyl group right there, and another alkyl group. So I actually have two alkyl groups here. So by Zaitsev's rule, I would predict that this would be my major product. It's going to be the one that is made in more abundance and is more stable. Now I'm gonna tell you guys something, and I don't think of Zaitsev's rule in the literal way it's defined, which is about alkyl groups. I just think of it as a reverse of Markovnikov's rule. And remember what I told you about how I remember Markovnikov's rule? If the rich get richer, well, Zaitsev's rule then is the poor get poorer. And so the way I approach Zaitsev's rule is to again just track hydrogens. Essentially then trying to decide who's most likely to lose the hydrogen. Well, if it's the poor gets poorer, it's the one with the least hydrogens in the first place is the one that's more likely to get poorer and lose them. And that was this carbon here, because it only had two hydrogens because it was already attached to an alkyl group over here, whereas this one had three. Now, if I remove the hydrogen and put the double bond right there in between, I'm going to get this product instead. And so thinking of it, the poor get poorer, is another way to reframe Zaitsev's rule, and it gets you the same product. You should approach it whatever way works best for your brain to help you get the correct product the most often. So let's look at a quick practice problem. Write the dehydration reaction of 2-methylcyclohexanol. These shouldn't have a space, they should be together. Showing the major product only. What is the IUPAC name of the product? So 2-methylcyclohexanol, I'm going to start by drawing my hexagon structure. And then I know that carbon 1, and it doesn't matter which one I pick as carbon 1, is the one with the hydroxyl group, and it doesn't matter which direction I go in this case because there's nothing else. Let's have this be carbon 2, and that's my methyl group. And I'm going to dehydrate them, which just like a hydration reaction does require an acidic catalyst and heat. The heat amount varies depending on what you're trying to get as a product and the structure you're starting with, so don't worry about that, just, heat. I'm going to go ahead and put in my hydrogens here because it's going to, or at least on a few of them, because it's going to help me out in deciding what my major product is. So I've got a hydrogen on each of these. Doesn't just that help me out? And I have some over here too, but I'm not going to worry about it. So I know that I'm going to get an alkene because the dehydration of an alcohol creates an alkene. So I already know that I'm going to end up with a double bond, and I know that I'm going to lose this, so I'm going to circle it. And I know that I'm going to lose it to make water because it's a dehydration reaction, so I'm going to dehydrate it. The question for what's the major product, because we're only focusing on the major product, is the double bond going to end up here because this hydrogen left, or this one, it doesn't really matter, or does the double bond end up here because this hydrogen left? So if I think Zaitsev's rule, the poor get poorer, this carbon here, carbon technically 2, this carbon here, carbon 2, the one with the methyl group, is already fairly poor in hydrogen and only has 1, as opposed to this carbon here, which is carbon 6, it has 2. So I'm going to assume this one's going to leave more often, and that's going to make my water. So then when I go to draw my structure over here, draw it as similar as possible. I'm going to put my methyl group right there. And this is where my hydroxyl group was. It's no longer going to be there. but I'm going to have, whoops, a very horribly drawn double bond in its place between what was carbon 1 and carbon 2. And what's the IUPAC name of this? So I can see this is, you know, cyclohexene. And then the carbon 1 is going to be, you know, the one with the methyl group, and then I can go through. So this is 1-methyl cyclohexane. Again, these should actually be one word. I don't know why I do that a lot. Well, what about the minor product? Because the minor product might actually be present, you know, 10 or 20%. So if the hydrogen had come from the other spot, let's just go ahead and draw it first, and then we'll figure out its IUPAC name. So here's my, I'm going to try to keep my structure. There's my methyl group. And if instead the double bond was placed here, so you'll notice these are different. You know, it might not be as easy to tell until we really look at it. So if I went to name this, I still end up with cyclohexene. But my numbering is going to be different. And if your numbering is different, that tells you you're dealing with a structural isomer. So in this case, this I'm going to make carbon 1 because my double bond gets preference over alkyl groups. So carbon 1, carbon 2, and carbon 3 then form my methyl. So it would be 3-methyl cyclohexane, which is a structural isomer to the major product. So Zaitsev's rule is really the other side of the coin for Markovnikov's rule, in the same way that dehydration of an alcohol is the other side of the coin for hydration of an alkene. I think looking at it that way and noticing the similarities can be helpful.